Hi folks, thanks for tuning into another honors geometry video with Mr. Murphy. It's finally time, folks. We're finally starting trigonometry. Just to give some background on what trigonometry is, again, mainly the way we'll be examining it is it's a set of functions that allow us to more clearly define a relationship between the sides and the angles of a triangle. At first, right triangles, and then eventually broaden it up a bit. And this is just the simplest version of the ways we can look at trig, because like I said in the past, you're going to be doing this for years to come. But for now, before we actually hit the new stuff, let's kind of recap what we know. That way we can more smoothly transition into the new stuff. So what we know, based on our similarity chapter, is that all similar triangles have equal ratios of sides. So for example, here I have these two triangles that are very clearly similar because of AA. They're both 20, 70, 90 right triangles. So what we could say, for example, is that the base to height ratio of the top one, A to B, is going to be equal to the base to height ratio of the bottom one, C to D. For instance, we can look at this in terms of very specific triangles too. Like I can look at 45, 45, 90 right triangles, which we talked about last time, aka isosceles right triangles, and say that the base to height ratio here is going to be 1 to 1. Because whatever one of these is, the other is going to be the same, because they're both legs and they're both congruent. It's kind of what it means to be isosceles. Whoops. Also, I could look at a 30, 60, 90, and depending on the way I lay it down, let's say that the 60 is the base. Sorry, the side opposite the 60-degree angle is the base. If it's a right triangle, that would imply that the other angle is 30 degrees. So we're looking at a 30, 60, 90. If I want to look at the base to height ratio here, well, what I know is, regardless of what the little side is, let's call it n, the little leg, the bigger leg is going to be root 3 times as big. So I can say the ratio of base to height is n root 3 to n, but if I even simplify that, it's just root 3 to 1. Which is to say that, again, the big leg, in this case the base, is going to be root 3 times as big as the little leg. We know this because we thoroughly examined 30, 60, 90s and 45, 45, 90s. We know how they go. But we haven't looked at 20, 70, 90s, or for that matter, like 50, 40, 90s, or like 27, 63, 90s, because why? Why would we look at all the possible different combinations? But of course, there's going to be common ratios between the different sides of those triangles as well. We just don't have any neat tricks like the whole like 1 to 1 and the whole like 1 to root 3 to 2 trick that we have for these. So then how do we end up finding the ratio of sides in those non-special right triangles? Well, we have a way. We have a tool, and that tool is trigonometry. In right triangles, trigonometry functions define relationships between its sides and its angles. Like I said, you're going to be doing this for a while, but once you start getting into Algebra 2, and even towards the end of this class, we can start to examine what it looks like to look at trig functions of non-acute angles, aka obtuse or right. But right now we're going to stick with acute angles, because we can look at it in terms of a right triangle. One of the trig functions that we're going to look at, the very first, is called the tangent. It being a function means that we take the tangent of an angle, and we say that the tangent of an angle is a ratio of its opposite leg to adjacent leg. So this right here is the symbolic form of tangent. We just say tan of A, where A is the measure of this angle at this vertex. So something that people end up getting confused about eventually is like, what does this mean to have tan of A? We should kind of think of this as like f of x, which is to say that our A is our input, kind of like our x is our input here in f of x. So just like if I were to say like square root equals 7, you'd be like, well, that doesn't make any sense. Square root of what equals 7? Because that's not how, I know the answer is 49, but the point is, the square root is a function that we apply to something. And I know that tangent sounds very like wordy here, but if we think about square root, that's kind of wordy too, right? Like if you ask someone what is the square root of a thing, maybe they're able to like articulate. It's the thing that when you multiply it by itself, it gives you the thing you start with. That sounds even worse. I'm sure there's a more formal definition than that, but my point is, even though we don't have like a formal symbol for it, like the whole like radix, I think that's what this is called, the tangent works in the same way, where we give it an input, that input being some acute angle in the triangle, and then the output is going to be the ratio of the leg opposite that angle to the leg adjacent to that angle. So in this case, if I'm looking at the tangent of angle A, it's a ratio, so it's going to involve a fraction, and the numerator is going to be the opposite leg, which for us is BC, and the denominator is going to be the adjacent leg, which is the blue one, which is AC. So in general, the tangent of any angle is going to be opposite over adjacent. And then in this particular case, it's BC over CA. So let's do some stuff with this. Let's actually talk with more concrete things, with like real numbers now. So if I want to, for instance, in this triangle jam, get it? In triangle jam, if I want to find the tangent of angle J, what I should be doing is setting up a ratio of the leg opposite J to the leg adjacent to J. Notice that the 50, the hypotenuse, isn't going to come into play here. I know the hypotenuse is adjacent to this angle. Like, it helps form it, right? But specifically now with tangent, we're not looking at any hypotenuses. We're just going to be looking at the legs, the opposite one and the adjacent one. Which means we kind of need to find AM. It's part of our whole process here. So what I could do is I could do the Pythagorean theorem and say 14 squared plus AM squared is equal to the hypotenuse squared, 50 squared. I did this ahead of time, so I know it's 48. So if I were to set up this ratio of opposite over adjacent with J, that tells me that it is 48 over 14, the opposite over adjacent, and then we can simplify that. They're both even, so they both have a common factor of 2. We reduce it to 24 over 7. Cool beans. No problem. Easy peasy. If I then ask for the tangent of M instead, well, here's M. And the way that it relates to the tangent of J is going to be, I don't know, kind of interesting. Opposite M is AJ, which is 14. Adjacent to it is, and again, adjacent leg is AM, which is 48. So this time we have 14 over 48, which is 7 over 24. So two things that we should mention about this and kind of note how the tangent of J and the tangent of M relate to each other. One is that, yes, they are complements. And that's because J and M, them being complementary angles, remember if this is 90, then the other two have to add up to 90. Them being complements mean that what is opposite to one is adjacent to the other. So essentially, we end up getting the reciprocal because opposite and adjacent are switched for each of them. Like AM is opposite angle J, but it's adjacent to angle M. So we end up with the numerators and denominators flipped. And another thing worth noting is that this triangle jam, is just a scaled up version of a 7, 24, 25 right triangle. So it makes sense then that our ingredients essentially simplify to 24 and 7. We would expect the tangent of J, for instance, to be the same as the tangent of, I'm going to call this like Z or whatever. Because if these are both, whatever these two angles are, if these are similar triangles, which we could deduce with SSS, if these are similar triangles, then we would expect the sides to be of the same proportion. So we would expect the same opposite over adjacent ratio. So keep that in mind. Keep in mind like why these two angles that are complementary end up producing reciprocal tangents. And note the whole like scaled up by a scale factor of 2 thing yielding the same tangent in terms of like the angles that correspond. So let's get even more concrete. Let's look at very specific examples, and honestly, we're gonna have to whip out our calculator. From now on, in fact, this is like part 1 of doing trig stuff. Part 2 is gonna come in class. I'm gonna need you to bring your calculator in class, like a decent one. Ideally, like a TI, like one of these bad boys. So thing 1 that we're gonna have to be able to do, and maybe even the hardest part of this, is setting up an equation. But this is kind of what makes it worthwhile. Like here are some like real life situations in which a tangent can actually be applicable for someone in like a STEM field. Story incoming for this one on the right, but let's look here. Suppose we want to find y in this left problem. Let's assume that this building is, a rectangle, in which case these two things would be congruent, and this is also y. So if I want to solve for y here, I don't have many ingredients. Like I don't have the hypotenuse, so it's not like I could do 120 squared plus y squared equals something squared. That's too many unknowns. But knowing that this angle right here is 41 allows us to use trigonometry, because now I can set up a ratio with the 41 degrees, the y, which is the side opposite it, and then the 120, which is the leg that's adjacent to it. I can say the tangent of 41, based on the definition of tangent, is going to be equal to the ratio of the opposite leg, which is y, over the adjacent leg, which is 120. Cool. So now we can actually get concrete and say, what does the tangent of 41 mean? Well, let's take out the calculator. Step 1, folks, and if you're doing this now, like, go get your calculator and pause the video. Like, pause the video first and go get your calculator, because I got to show you something that you're going to have to do. In mode, like mine looks like this, but if you have an inferior TI, there should still be a mode button. You want to make sure that if you have an option to measure your angles between radian and degree, for you it might say rad versus deg or something. Make sure it says degree. A radian is another way of measuring an angle that you deal with in the upper maths, like calculus. Typically in physics, you're going to use degrees more often than radians. So if you're taking AP Calc and AP Physics at the same time, you're going to drive yourself crazy having to remember to switch back and forth. But in this class, for now, for the most part, we're going to be working in degrees. So make sure that your calculator recognizes this by having degrees selected in mode. And then to get out, press second quit. And now we're back. So let's take a second to actually look at this. Tangent of 41. And we know it's degrees. And by the way, sine, cosine, tangent are trig functions. For some calculators, they're going to be right here, just like right on the like a home button. You don't have to press any fancy buttons to get there. On some calculators, you might have to press like math or something. There might even be a trig button. It might say trig, but do yourself a favor and find the tangent button. When you do, it's going to give you an open set of parentheses, like what's the input? User, what am I taking the tangent of? And then that's when we tell it, 41, please and thanks. And we close this up. So this produces for us 0.86928 blah, blah, blah. This is an irrational number. This is going to go on forever. This is not the exact figure for the tangent of 41, but it's our calculator's approximation. It looks like it rounds to 10 decimal places. Fine. So the way to interpret this, what we should say from this is that the opposite to adjacent ratio is essentially 0.869 to 1. What that means is basically that y is going to be like 87% of 120. Let's think about this for a second. This angle right here is 49 degrees because it has to be, because this is a right triangle. So since 120 is opposite the 49 degree angle, we would expect it to be bigger than y, because y is opposite a smaller angle. Like bigger angle is opposite bigger side, smaller angle is opposite smaller side. So that indicates that y is going to be smaller. And how much smaller? It's going to be like 87% of it. So let's not worry about this value for now. Let's actually finish the problem here. If I want to solve for y, what do? I know you know what to do. You multiply each side by 120, right? So what I end up getting is that 120 times the tangent of 41 is equal to y, because these 120s cancel out as we need them to. What we could do is we could end up kind of swapping the sides of the equation here to get y is equal to 120 times tangent of 41. And then we don't have to worry about this thing right here. Like, I threw this out here just for some context, just so you know what this actually even means. But I could do this whole phrase, like 120 tangent of 41, all at once. Watch. 120 tangent 41. This, when I do 120 tangent, this implies I'm multiplying them. And it tells me 104.314. Just for me to be a stickler here, I'm telling you to round to 3 decimal places, but it doesn't matter that much. And yeah, there we go. That tells me that the height of this building is 104.314 meters. Great. This is a really useful tool, whether we recognize it or not, because we can deduce more from triangles with little information. And as you can imagine, we can pretty much draw right triangles anywhere in the world. For example, I have a student, or a former student, who I had for Algebra 2 back when I taught that class, who went on to be like an Air Force pilot. And one year he came back and visited, and we were just like talking or whatever. And he was talking about how he flies planes all the time. And like as a joke, I was like, oh, dude, I bet you use trigonometry all the time. And he very seriously, like totally unironically was like, oh yeah, almost every day. Because when you're talking about things like, you have a lot to worry about when you're in an airplane in terms of like the angle of which you're declining. That's called the angle of depression, like how south of horizontal you are. Especially if you're like pulling onto a runway, you don't want to go too steep or not. You want to really worry about like, all right, if my altitude's 1,000 feet and this is my angle of depression, if I'm going back to Earth at this angle, like, do I have enough room on the runway? Like, how much room am I going to need? These are real questions that like real people, like scientists and engineers, need to worry about. So let's actually consider this problem. Let's see like how much runway this plane actually needs. And again, the way we want to start this problem is the way we started the previous one. Try to set up a relationship here. Let us assume that this plane is, whoops, I don't know why that happened. Spoiler alert. Let's assume that this plane's initial path was horizontal to the ground. It maintained an altitude of 1,000 feet. So what I could say is that this angle here, 25 degrees, I could do stuff with this. I could say that the tangent of it is equal to opposite over adjacent. The leg opposite is 1,000. The adjacent leg is z. I don't need to worry about the hypotenuse, so I get tangent of 25 equals 1,000 over z. Opposite over adjacent. So the way that this problem is different than the previous one is that this time our denominator is in the, our variable is in the denominator. And for some reason that just messes people up. And I bet right now, think about how you would try to solve this problem. Would you multiply each side by 1,000? That's not what you do. That won't cancel this way. That'll just complicate things even more. Would you try to divide by 1,000? That really wouldn't work either, sorry, because z is still in the denominator, and that's not helping us get any closer to z equals something. So think about what we would need to do in order to get z isolated, to solve for z, to get z equals. What I could do is I could multiply each side here by z. That's one thing I could do. Because I've now removed it from this right side's denominator, because z over z is 1, and now I'm looking at this quantity. Great. I still want to get z by itself, so the next thing to do, or so it would seem, is divide by the tangent of 25. Remember, whenever I feel like it, I can go into my calculator and find out what the tangent of 25 is, but I'm going to save that for last, because it's some really ugly decimal, and I don't want to worry about it until the very end. And if I do that, this cancels, and I'm left with z on the left. On the right, I'm left with 1,000 divided by tangent of 25. So, just to recap, the tangent of 25 is equal to 0.466. What that means is this opposite leg, the 1,000, is like 47% of z. So I would expect z to be like a little bit more than twice as big. Like if this is 0.5, that would mean that 1,000 was half of z. So in this case, it's less than half, so z is going to be a little bit more than that. Let's find out. Let's find out if I'm talking nonsense or if I know what I'm talking about. Z is equal to 1,000 over a tangent of 25 degrees. And that is, yeah, a little more than 2,000. God, I love being right. I'm so good. 2,144.507 feet. 3 decimal places. Feet? Yeah, feet. Great. You might be wondering to yourself, what if... You know what, you're probably not wondering this. But if you were, or if you are now, what if I want to rope the 65 degrees into this? Because if this is 25 degrees, this is 65. Certainly I can make a trig problem with this. And the answer is yes, you can. I could say the tangent of 65. Sometimes people don't always put parentheses around this. We just say like tan of 65 without it. That's equal to opposite over adjacent, so z over 1,000. So yes, it is the case that z is equal to, if I multiply each side by 1,000, 1,000 tan 65. Which, guess what? If I'm correct, which of course I am, I always am, except when I'm not, 1,000 tan 65, look at that. It produces the same answer. So this is one of those cases where, depending on how you set up the problem, it might look different than someone else's next to you, but you should be getting the same answer at the very end of the day. Let's just do like a couple more. I'm going to say at this point, if you want to pause the video and try these, that's a good idea. Again, make sure you have a calculator. Make sure you can find the tangent button. Make sure that it's in degrees instead of radians. And pause if you have to, but I'm going to go on right now. One way to set this up, unless you want to involve like 19 on the top here. You could do this with 19 also, but I stuck with the 71. And I said, tangent of 71 is opposite leg over adjacent leg, so 11.2 over y. I did that whole thing where, I guess I should have noted, the end result on the previous page with this stuff was that the tangent of 25 and the z kind of just like switched places. So that's a little bit of a shortcut here. Like if I multiply each side by y and then divide each side by the tangent of 71, it essentially has the same effect as just swapping these two components in the equation. So I could get that y is equal to 11.2 over tangent of 71. Trust me, I put it in the calculator. It ends up being 3.856. Which again, like, throw this back in the problem, make sure it makes sense. It's approximately 3.856. 71 degrees is significantly bigger than 19 degrees, so it makes sense that the side opposite the 71 degrees is significantly bigger than the side opposite the 19 degrees. And it is. Same thing on the right side. If I want to set it up, I could do tangent of 32 equals y over 15. That's, again, relative to this angle, opposite over adjacent. And we end up getting, as a final answer, 9.373. Cool. If you want to pause this, go ahead. I'm just going to show the answers to this. But I guess the starting point with this would be noting that if this is 48 degrees, this right here would be 42 degrees. It would have to be because the triangle sum theorem, or the triangle angle sum theorem? I don't know, whatever. If I stick with that 48, I could do, if I call this x, tangent of 48 equals x over 6, and I could solve for that and get that it's like 6.664. And then the only thing that we don't know is the hypotenuse. But at the end of the day, this thing's a right triangle. So if we have everything else, if we have the two legs, we could get what is approximately the hypotenuse. I know this is a rounded value, but if we're not rounding to that many decimal places, it shouldn't be that big of a difference. If we do the Pythagorean theorem, then h is approximately 8.967. Again, check that things are proportional at the end by noting that the biggest side is the hypotenuse. The side opposite the 48 is bigger than the side opposite the 42, and everything checks out. So I'm going to leave this last one for you to kind of think about before the next time I see you. But here are some values that we won't really need our calculator to calculate. The tangent of 0, the tangent of 45 degrees, and the tangent of 90 degrees. These values, the tangent of 0 is 0, the tangent of 45 is 1, which you might be able to think about why that is if you draw out the triangle that goes with this. And then the tangent of 90 is undefined. Think about why this is, and then the next time I see you, we'll have a nice little conversation about it. But this video is running pretty long as it is, so thanks for watching, folks. Appreciate it.